All right, good morning, everyone. 9:10 here, so let's begin with today's class. So the goal for today is that we finish the terrain exercise, which we were pretty close to. And then we're gonna start talking about soil electroconductivity on the second part of the class. And just go into that topic a little bit in more depth before we actually do the coding of that. Okay, so again, I'm just showing you here the folder where I have the current terrain analysis. I'm just gonna launch that RStudio project icon. So again, always launch through the RStudio project icon. Do not simply double click on a script because that may open a script on a different project than what you intended. So just to make sure your relative paths are working all right, always launch your RStudio using the RStudio project icon. And just a reminder, if you are online, please turn on your camera. Okay, so we stopped. Let's see, if we come here on the side, toggle on and off your outline. We stopped last time, I think was on the flow there chunk for the flow direction. I believe that's where we stopped, and we were doing the plot, and this is where we had some divergences between what I was getting and what you were all getting. If you come here to the flow there map 2 chunk, which we still have to develop that, but if you just come to that and you say run all above, that is basically going to run all the chunks above and make sure that you have everything in your environment that we're going to be needing. So I'm just going to give it a moment for mine to run. So I see here, my console is at top right. I'm seeing that things are happening, and then finish running. And before we talk more about things here, I just want to tell you that it was really interesting, and I think this is something that this class partially addresses, but not fully, because we just don't have the time. But I was telling you about like reproducibility, right? So if you give your data and your code to someone else, they should be able to reproduce what you did exactly. And then we saw that not happening last class. And I went back to my office. I tried to troubleshoot and understand what was going on. And it was really when I installed the packages, I did that for last year's class. And you all installed like this year for this class. And so you had the latest version of the packages, and I didn't. And that's what was causing some of the differences. And 2 packages were actually causing those differences. So one of them, I forgot now. I told you in the email which one. I remember Virides was one of them. So Virides was the one responsible for the breaks showing up differently, even though we had the same break specification here on the code. So that was one of the differences. And the other one, I don't remember now which other package it was, but it was also a package that was causing things to be different before getting to the plotting area. So I guess, with that, it's just interesting to think about it, that we need the code and we need the data, but we also need to make sure we have the same software versions. And that goes all the way from like your operating system, our RStudio package versions, all that. Of course, sometimes they're different and it doesn't make a difference on the output, but sometimes if there are divergences, especially in the case of package versions, that could cause slight differences in what we're seeing. So that's also part of reproducibility workflow. So in this class, again, we're talking mostly about reproducibility as it relates to same code and data. We're not taking any measures to make sure our packages are the same versions. That's a topic for a different class, but just wanted to bring that up since that happened last class. Okay, so one thing that you're going to learn on the quiz that's going to follow after we finish the next chunk here, and the reason why I wanted these specific breaks here is if we don't have these breaks specified, I'm just going to delete on my side so you can see. If we don't have these breaks specified, the breaks that it creates is just like whatever it decides that is a good break for this data. And the reason why I had those specific breaks specified here is because when you are going through the what I'm asking here in the quiz, you're gonna learn that flow direction is basically, it is a numerical variable, but it can only take values that I specified in this break here. So 1, 2, 4, 8, 16, 32, 64, and 128. They mean different things. And really right now, if we just look at this map, you don't know yet what they mean. And the thing is, they don't simply mean, it doesn't necessarily mean that one is better or worse than 128. It's just the way that they're configured. And again, you're going to be learning what that means when you do the quiz. But that's why I wanted to specify them here, because otherwise, even though every cell here has one of these values, R looks at it and thinks it's numerical. So it just treats as, instead of an integer like a class, it just treats that as numerical. So it gives us, the impression that we see on the map is not exactly the most helpful.
And coming up with the specifications of those values, what did you base on?
So I decided to do these specific breaks. And again, this is just for visualization, right? So this is not changing the data. It's just how I want to visualize. But this is going to be based on what you're going to learn on the quiz. So I'm not going to fully answer that yet. I'll wait for you guys to do the quiz first, and then we talk about it. But what I can say is basically that each one of these values here is representing a direction of which water is moving. And right now, I don't want to tell you much more than that because I want you to also learn through the quiz. But what I want to do is, if we just look at this map, as I have here, as you all have, I mean, we see these different values, right, on the scale. Right now, again, they don't really mean much, but it's kind of difficult. The only thing that I can tell you at this point is that these represent different directions. But this is not degrees. It's not like east, west. It doesn't have anything to do with that yet. But just so you know that each value here means that water is going to a different direction. And looking at that from this perspective here, for using this plot, perhaps is not the most clear way of really seeing, oh, this is the direction that most points are going to or not. So I want to show you a slightly different way of looking at the same data and perhaps being able to learn better, at least like thinking of these different classes, which direction water is moving in this field, even though this doesn't tell us yet what direction that is. But that's going to be for the quiz. So again, I do want to plot this a little bit differently so we have a little better insight into how these different classes are distributed in this field. And that's why I have this next chunk here. So if you just come to the next chunk, we're going to do some more plotting. So I'm starting with ggplot. I do want to bring this layer again, and just to remind you, this layer here is called flow_dir. So I just want to come here, add a plus. It is a stars object. So again, we use geom_stars for that. And stars object is related to a raster. So it's still in raster format. We say data equals flow_dir. That's the name of the object where this data is. I just want to print that below so you can see. And this object, so again, raster objects, and in this case specifically stars objects, they don't really give you a nice data frame that you can look at the cells like SF objects do. They only give you a summary here of like a statistical summary in the name of the column. So the name of this column is flow_dir, that actually contains those values that we're seeing on this map here. And again, this column here is seen as numerical. And because they could have been called A, B, C, D, E, F, G, and it would still mean the same as far as what they represent on the map, meaning that they could have been treated as a categorical variable or a factor variable. If we I'm just going to run this so you can see what happens. It's basically, at this point, is very similar to the plot above. It's just that the plot above, we had done more, fine tuning to the plot, whereas now, but it's still the same information. And what I want to do here is force R to see these values as individual classes instead of treating as numerical. To do that, I don't know if we have done this yet in the class. I think we did maybe in the wrangling exercise. I want to, so right now this column is numerical. I want to transform that to factor. To do that, there is a function called factor pretty much that we can use. And I want to do that here kind of on the fly. So I'm going to be doing that in the data set right here and not save it to any object. So that change is not going to be saved to the object flow there. I just want to do it on the fly for this plot only. So if you have your data right there, you can just add a pipe. We're gonna do a mutate. And I want to call this column still flow there. So I'm just basically overriding the column flow there inside of the object flow there. Sorry if that's confusing. And then there's a function that for us to force this to be categories, the function is called factor. And then inside of that factor function, we just say the column name that we want to transform to factor, which again is flow there. So, you know, I know that it looks kind of crazy right now because there's a whole bunch of things going on, but we're starting with the object flow dir, which inside of it, it has a column called flow dir, and we're just transforming that from numerical to categorical using the function factor. And again, so if you think of it, this entire, what I'm highlighting right there, it's what's being interpreted as the data for this layer. This change, again, that we're doing is not being saved to any object. It's just like on the fly, we're doing that just to force R to see this as categories instead of numerical and continuous data. So if we just go ahead and run that, this is what we get. So now you can see that even though we still have a color scale, but now R is really showing us those classes because those are the individual values found within that flow dir column. Even though R was seen as numerical, now we're forcing it to see as factored. And I think that it's not as helpful yet, but it's going to become very helpful in a moment here. Okay, so the next thing I want to do is just bring in the boundary. So I want to add a plus. I'm going to use geom underscore what to bring in the boundary. Alexis, what do you think? So one way that I would do to find that out is if you, so the boundary object is called boundary W that we already like brought up upper on the script. If I just print that, at least I know what type of object it is, right? So it is an SF object, as we're seeing. So it's not stars. It is like a boundary. So it's a vector. It's an SF object. Does that help? Geom SF, right? That's correct. So we add a plus. We do geom underscore SF because that's an SF object, it's a vector file. We say data equals boundary W. If you recall, if I just run this, the boundary, it puts the boundary there, but the boundary has a fill by default. And I do not want that to have a fill because I want to see through it. I want to see the data behind it. So we just come back to geom SF, add a comma, and we just say fill equals NA. So it basically only gives us the outline, but no fill. Let's see here. What else is important on my cheat sheet? So I do want to change here the theme. So if you recall in the beginning, we had a special theme that we created. So we can just add a plus, and the name of the object with our theme is called my theme underscore map. So if we do that, this is what we get. Okay, so I just want to stop for a moment here and tell you that right now, even though colors are different, the way we're seeing this map is still pretty similar to what this is. It's just a different color scale. And the fact that now we see in pink, we see, again, this flow dir object is a raster object of type stars. And here we can really see how outside of the boundary, it's all coded NaN, which means not a number, but it's, you kind of think of as an NA value. And again, raster is always like a continuous layer. Even when you don't have data, that cell is still there. It's just coded as an A or NaN. Whereas vector, it doesn't work like that, right? So just remember that. So one trick I want to show you here, which can really be used for any ggplot to do, doesn't have to be geospatial, but I want to show you here is if I wanted to create a separate map for each one of these categories. Okay, so let's say I wanted to only have category 1 here, so flow direction level 1 in one plot, and then the next plot just category 2, and next plot just category 4, and so on. How, like, based on what you learned through this class already, or maybe through your different experiences with art, if that's your case, how would you do that? How would you create a map for each one of these categories? Anyone has any thoughts? Like, if I gave you this data and I said, make me a plot of only category 1, what would you do?
You can say more than make it ending. It's like for 2, 4, 8, we can remove, say that doesn't show that color and just show only one map.
Okay, so Amrinder is suggesting that maybe we could use a conditional sentence to say, if it is different than 1, then make that be an A.
Yeah.
Okay, so that is one way to do that. Any other thoughts of a different way?
Whether you have to go back to the case when,
Okay, the case when and do what?
like create those conditions and then make different maps based on those conditions.
Okay, so that's kind of what Amrinder is saying as well with using some type of conditional, right? Like on case when. So that's one way. And anyone, I heard online.
Maybe we can use the filter function in the data, like GeoMStar, the data we are feeding is flow dir. So on that section, we can filter the data based on the classes or like that.
Yeah, so that's also an option, right? So one option would be to do a mutate and basically say if flow dir is different than 1, just treat everything else as an A. Another option would be to filter, so not to change the data, but just to filter the data, right? So the difference here is that what Amrinder and Dennis are saying, using like a conditional statement on the mutate, we would basically be changing the data and still end up with the same number of rows. It's just that most of them are going to be an A's now. Anything that's not 1 is going to be an A. What Sekar is saying is, like, if we do a filter, we're not changing the data cell values, but we're just decreasing the number of rows to only contain a certain class. Yeah, I think that those are probably the 2 ways I would do as well. And in both of those ways, if you think of it, it would be a little bit of work to get this to happen, because you would have to, let's say if we go the filter route, I first do like create an object where I filter only the values 1, make a map. And then I go on the next chunk, create another object that I just filter the values 2, create a map. So just duplicating a lot of code to get different maps, right? I want to show you a way here that is actually a lot easier than that. So if we just come back to the code, we just add a plus. ggplot has a few functions that begin with the word facet. We're going to be using facet_wrap. The way that this is you give it a column name for this function, and it basically looks at all the different values within that column and creates a map for each one of those levels. So here we're basically going to say that the way that we say what column it is we need to give it a tilde, so that squiggly line, and say what's the name of the column that has these values, which is flow dir. Right, the one that, and again, remember that now this flow dir is basically the one coming on this data here, which we transform to factor to categories already. So if we just go ahead and do that, this is what happens. I just want to quickly show you the code, but also quickly like increase this so you can see. So facet wrap did exactly what we were talking about, as far as it looked at the column that we gave it. So we gave it the column flow dir, and then it created a map for each level of flow dir. In this case, going from 1 to 128, including the not a number level, which I think is pretty interesting. So this is something I'm showing you this function here in this context. And again, this is data visualization, is not data wrangling, is not analysis, it's just visualization. But I want to give you another example of how I use this facet functions to show multiple things. Let's say you have, so I had for my PhD, I had a study where I had like 30 different sites, and I had the same study conducted over 30 different sites. And I had this huge data set where one of the columns said site name, right? And now I wanted to show this data by site. And originally, if I had to use a filter function, I would have to basically do a filter by site, create a map, and so on. But then if you're just on the visualization side, if you just want to show a map or not a map in that case, because it was not geospatial, but just a plot of like a box plot or something, or means, I could simply just say facet wrap by site, and then poof, I have 30 plots in front of me with one line of code, right? So that is just one function that's very, very useful whenever you think, oh, I wish I could make one plot for each level of whatever column it is. It could be site, could be year, could be soil depth, could be whatever it is. So I just wanted
So,
to.
Dr.
Yes.
So I've been following along with you and everything, but I just want to make sure I understand this correctly. Can you explain what these points represent?
Yeah, okay. So this is actually something that you are all going to explore on your side first, and then we'll come together to discuss. But for the quest that is happening, like right after we end talking about this plot. So I guess I would say, if everyone was able to make these, I think you're gonna have to have this plot here to help you answer one of the questions of the quiz. But what they mean is something that you're gonna learn during the quiz. So we're gonna hold on that thought, and then once you all submit the quiz answer, then we'll come back and discuss that as a group. But basically what I wanted to show you is, maybe here is easier, whatever 1 and 128 means, at least here we can see which class is the most predominant, at least visually, right? So, I mean, at least I could tell you, and I'm hoping that you probably can also just visually see here which class is the most predominant on this field. And you don't have to tell me that now because that's part of your quiz. Okay. So, I just want to show this plot here because I think it helps to separate those classes and see them individually in the map. So here's my quiz for you, which we're going to do right now, and I'll give you maybe 10 minutes or so to answer, and you can send your answers to my email I'll just put that up in the screen here. So it's alanbastos@uga.edu. So here's what I'm asking you. I want you to look at the map above and tell me first, which one of these panels appears to have the most data points? Just based on looking at it, you don't have to do any extra calculations or coding, it's just looking at it. And then I want you to then dig a little bit into the documentation of a function. And because you're going to learn when you do that, which cardinal direction is related to each one of these numbers that right now are not cardinal directions, they're not degrees, they're just numbers. And I want you to translate that into that cardinal direction being, one of the ones that I'm listing up there. And I want you to tell me which of those directions is related to the answer you gave above. So if you said that, I don't know, if you were to tell me that maybe, let's just go with one obviously wrong answer. If you told me that 8 was the most, the one that had the most points, then it would tell me what does 8 mean when you translate that into a cardinal direction. And that's pretty much it. It's a pretty simple quiz. So I have 2 questions for you, where one, you just tell me the number, the other, just tell me what direction that number represents. And then, the question that you all are having is, how do I even know that, right? And
Dr. Bastos.
Yes.
Quick question before we get started. Just to double check. So when looking at the top left, right, and bottom of the map, is that could you make sure that we're understanding the same north, south, east, and west, like it's top north?
But you don't know
of the
that
field?
We haven't talked about that yet. So
But how are we gonna answer that question? Because I thought that was what you were. I just think I'm a little confused here. Do you see what I'm asking?
Yeah. So right now, these numbers here mean nothing as far as direction. You're gonna learn how that translates, how those numbers translate to a cardinal direction when you read the documentation of a function, which is part of the quiz.
So you have to mention one number or you mention two?
Yeah, so you can just tell me one number, like what is the most, so in the first question, what's the class here based on a number? So you can tell me, let's say 8. 8 is the one that has the most points, which is clearly not, but and then you tell me, what does 8 mean in a cardinal direction sense? And how are you gonna learn that? You're gonna learn that by reading the documentation of the function that created these values. So I just wanna, I wanna tell you that that function is the function terrain. So if you recall, when we did flow there, right? So when we created the object flow there, I just wanna go back to that chunk is right here. So that's where we created it. And the column flow there was basically derived from when we ran this function here, function terrain from package Terra. So this function here is where you're gonna find explanation of everything about this function, including its output and what it means. So I basically want you to look into the documentation of that function and look for that answer there. We haven't done this much yet, but part of this quiz is just to get you used to reading documentation of functions, which in R, we just use the function help and then just call the function name within quotation marks. And that pops up its documentation here on the right. So look into that documentation, read through it, and you're gonna find the answer to question 2 here. So I'm gonna give you 10 minutes, maybe here, just, the answer is pretty straightforward, just gonna be one direction, right? So your answers are pretty short, but how you get to them, we're gonna do some reading. So again, do go through the documentation of the terrain function. And then you can just send me an email saying a number and a direction, and that's all I need from you. So I'm gonna put here a timer for 10 minutes. Maybe you're not gonna need that much, but we'll just start with 10 and go from there. Right, 1 minute left. All right, our timer's done. Yeah, I still have some of you that are still need to send me. I'll give you another minute just to finish submitting, but I do want to have everything in before we start talking about this. So make sure you submit in the next minute. Okay, so we're gonna have to move on. You know, just send me, if you haven't yet, just send me your answer. And we're gonna continue here because we're gonna talk about this and, you know, I want you all to have answered without hearing the discussion first. Okay. So why did I ask you to do that? Why did I not simply went ahead and told you what those numbers meant? First, because I thought that was a good case for us to go through, you know, the documentation aspect of things, which is not something we have done a lot in the class. However, if you do plan to continue using R or maybe even other programming languages, being familiar with documentation is important. So I thought this was a good exercise for us to do that, especially with the terrain function, since it's doing so many different things. So I just want to do what you did here, ask for help and look into the terrain function. Again, you can ask for help for any function, and most functions in R are very well documented. And I just want to show you here most functions in R will have a similar structure where it gives you a description first. So it tells you what this function generally does and some details about it. It gets into, so these headings, description, usage, arguments, details, and example are always there, or like 99% of the time functions will have it. And it's just, I just wanted you to become a little bit more familiar with them. So, you know, you probably came through and you saw, so on usage, it basically tells you quickly, like, what are the arguments there, and whatever value it says here on the usage is going to be the default value for that argument. So if you don't change anything, you're getting these values here, which are the default values. However, it does then have an arguments list where you can look into it, see what argument names are available for you to change, and then it gives you a description of what they are. And some of them we can change, right? So as we saw, V here was the what were the options of what we wanted to calculate. So you could change to slope, aspect, DPI, TRI, roughness, or flow direction. And then it has a note here, see details if you want to know what those mean. We also changed the unit a couple of times. So for some of them we did degrees, for others we did radians. And it has some more details here that, you know, you didn't need to know at that point. But then if you do come on details, it really tells you, in this specific case of this function, how it is calculating things, right? So how is it calculating slope, aspect, and flow direction based on elevation? Especially for graduate, I mean, this is important for everyone, but most importantly, if you're planning to publish a scientific paper and you go on a paper and you did, you know, you use elevation to calculate slope or aspect, maybe a reviewer may come back to you and say, how did you calculate that? And if you just ran a function that you said terrain function slope, you really don't know how that was calculated because it was behind the scenes. You didn't do that yourself. So the way that you would know would be to come on the documentation of this function. This function here is very well documented because it gives you even the references of the papers that it uses and what it implements behind the scenes. So if you need to come back to someone and say, this is how elevation was calculated, you can give them this reference of these papers, which here's the citation, but then you do have the reference under the reference section. So this function is very well documented. It even gives you scientific references for the methods it uses. And then normally on details, it also explains some other things related to what the results that you're seeing or what is returning to you as an output. In this case here, what I was hoping that you would have done was to get to this part of the documentation where you would read, you know, what flow direction means and what those numbers mean. So, I mean, you know, all of you answered by this point. So I hope you all got to this point. I was just browsing through the emails. Most of you got it right. So if we see here, for a given pixel, right? So let's say we're looking at pixel X in that raster. It basically looks at all of its neighboring cells, and wherever you have the most difference in elevation, that's where water is moving. And it just tells you a number, again, going 1, 2, 4, 8, 16, 32, 64, 128, just going around that pixel and just coding them as a number. Again, these numbers here are not angled, right? So they might as well just being named A, B, C, D, E, F, G would mean the same thing as far as we are thinking about them. But it's just that if you look here and I tell you that this pixel in the middle is going in direction, let's say here 64. So that would be the greatest difference in elevation. That's where water is moving towards. What cardinal direction would 64 be? In this case that I'm giving you, this example. North, right? Exactly. 64 here would mean north because you're moving from X to 64. That's in a north direction. What about if they were moving in direction 8? Let me ask somebody online. Maybe Sarah, what do you think? If I tell you that if 8 is the value, which cardinal direction is water moving?
Southwest.
Sorry, can you say that again?
Southwest.
Southwest, that's right. That's perfectly right. Thank you. Yeah, so I guess that's what I wanted you to learn from documentation and then, think about the answer here. So I think all of you got it right that class number 1 here is the one that has the most points or most pixels fall within class number 1. And then let me ask someone else. So in this case here, class number 1, what direction does that mean? What cardinal direction does that represent? Maybe David, what do you think?
East.
East, right? Yes. So that 1 represents east here, and meaning that water is moving mostly in an eastern direction, right? So for all those pixels, water is moving east.
Dr. Bastos,
Yes.
I ain't gonna lie to you, this is not clicking me. I'm not understanding this cardinal direction thing. I'm just gonna, I don't know if you can maybe re-explain that but I'm not following you here.
Okay, let me see. Let me try to see how I can explain this differently. So let's say if you think of so the way that the algorithm is working is getting to a pixel, right? So let's say you go to the middle of the field and you're sitting on a pixel, right? And then you look around you on all of your neighboring pixels, thinking that you have, in that case, so 1, 2, 3, 4, 5, 6, 7, 8 neighboring pixels all around you. And if you could go to each one of them and take elevation data and then compare to the original one that you are in the middle, and then you can look at which pixel has the most difference in elevation, right? So let's say if we're sitting on X, on pixel X, as documentation says, and you realize that of all your neighboring pixels or areas of this field, the one immediately if you're facing north, the one immediate to your right has the greatest drop in elevation. Then you're assuming that that's where water is moving into or moving towards, right? So from where, if you go to your pixel and you drop a bucket of water, or maybe more than that, where would water move in that case? From your pixel, which pixel would that move into? So if it says it's moving into 1, it's going into that direction, right? Into that right direction if you're facing north. And what perhaps wasn't completely clear from the documentation, but I wanted you to think about it is if this is what you're seeing, if you could just rethink of these numbers instead of being 1, 2, 3, 4, 5. Think that instead of having these 1, 2, 4, 8, and so on, you had actually 1 would be east, and then 2 would be southeast, and 4 would be south, and so on, assuming you're facing north.
Professor, it could not be rotated, then also.
It could be,
If we rotate the 1 on the south direction, or it will always be 1 on the east.
The way that this algorithm works, it would always be this way. Of course, if you want to come up with your own algorithm, you can code it whatever you want, right? You could even call it give the actual cardinal direction names if you wanted, which would be more clear.
Professor, I have a question.
Just give me a second. Can you guys online just hold them for a moment? We have a question here in Athens, and I'll get back to you in a moment. Yes, Henry.
So when you're viewing it like we are right now, the very top of the map is the north and the very bottom is the south.
Yes, okay, that's a great question. So Tyner was asking, can we always assume that when you're looking at a map in R, that you're looking at based on having north being facing, the map with the north arrow facing north, actually. That is normally the default of GIS, right? So every time you pull them, I mean, you can even imagine like if you go Google Maps or Waze or whatever, the default is that you'll be facing north. Of course, if you're getting directions is a little bit different because it will change as you're moving, right? But any GIS having a northern facing direction is the most common one. And normally, that's also a good question to follow up on because we have not done this yet. Maybe we're going to show you this later, but it's really good practice to always include a north arrow in a map. Normally, we show maps with a north arrow facing north anyways, so that's kind of implied, and that's what's happening with us here. But sometimes, depending on like, oh, I have this just weirdly shaped field that if I just put in a paper facing north, it makes no, like it's hard to fit on a page. Maybe you want to rotate the field just to fit easier, like on a page or whatever it is, a presentation. And then it's really important you show the north arrow because now north is not facing north, right? North may be facing any other direction. Then that's really important. But the default, it's pretty safe to assume that's always facing north. Yeah, so I know online we had a couple questions.
Yeah, so can I go ahead?
Yes, go ahead.
So in this very example, the panel in the description, it's like exactly the same in the label. But let's say we have different breaks. Let's say 10, 20, 30, 40, 50, so on. But the description would be same. So I just want to confirm that we will build this panel in the same way. Like we will put X in the middle, and then we will divide our whole legend around like this. Can you comment on that?
Yeah, so again, like the numbers that we're seeing here are a function, are a result of what the function gives us back, right? And what the function gives us back is this. And this is the main reason. Let me just come back here to the previous map and just show you. So on our code of the previous map, this one here, I specify the breaks to match what the output of the function was. If I remove this, that breaks argument and just rerun this, R looks at that column flow there and it sees that there are a whole bunch of numbers and assumes that this is a continuous variable. And because of that, it creates its own breaks, right? So
yeah, actually, that's my question. So let's say we are working with a data set and you intentionally put those breaks which match the description. But what if it's the case like we cannot do that, we don't have that same breaks? What will we do in that case?
So in this case here, it's a little bit trickier to think about it just because to understand what that float their value really is, right? Which is more a function, which is more of a problem related to the function itself and what is given us back than it is anything else, right? It's just, in this case here, if we go through the documentation, we do see that the cells can only be one of these 8 values. There's not going to be a cell with a 3. There's not going to be a cell with a 5, right? It's going to have to be one of these levels. So that's how we create the intuition of how can we plot this and make more sense. So just to give another example. So here, the way that I transform basically these cell values that I know are the only possible outcomes for this from this algorithm, I transform that into a factor, into a category, which now it looks at each unique value inside under that column, and then treats that as a category, meaning that one could have been named A, and it would have, as far as we're concerned, the same meaning. So it does not mean that one is less than 2, or in this case, right? It's just giving you a direction based on the center pixel.
So is it okay for me to assume like if in future I have to find flow direction of any data set, then I will use the same breaks for all the maps?
Yes, you will use all the same breaks because that is how the output of the function is given you. Of course, if you use it, let's say if you use a different function for flow direction coming from a different package that treats this coding differently, like let's say maybe you use a package that instead of giving you the numbers actually gives you east, south, and so on, then that's a lot easier, right? you don't have to do that extra step of interpreting what a number means in cardinal direction. So always it was more of a matter of going back to the documentation and understanding what it is doing and what do the values is returning you mean, right? That's what this exercise was about, is for us to understand and create that understanding.
All
But-
right, I got it. Thank you.
Yeah, but every time you use this function and you ask for flow direction, you will always get one of these 8 values for each cell.
Dr. Bastos,
Yes.
using that example you've got up there, could you kind of explain the scale a little more for me? Because like, let's say you're standing on X and and your point directly to your right was completely level with you. What would that number represent versus as compared to something that was higher up and lower down?
So you mean like if I'm on X and then everything else at the same elevation?
Or maybe just one point necessarily, just like what number necessarily represents the same elevation and versus lower elevation and higher elevation?
Like if you were in a laser level field like they have out of Mississippi, what number would represent that?
So if you have a field that's completely leveled to the point where your elevation data cannot differentiate elevation differences between neighboring pixels. So let's say everything was at the same elevation, right? So if you're sitting on X and X is at, let's say 40 feet and everything is 40 feet as well. I believe, and we can go back and reread this documentation here, but I think that if that's the case, so if the case is that like water is either not moving or you have maybe 2 cells that could move into, I think it just does a random selection of the candidates. So let's say if everything is equal, especially to the middle and water is not moving, I think it would still return you a value. Like it would still randomly return you a value.
Yeah, of course, that's what is written on there, that, like, if 2 cells have the same drop.
Yeah, perfect.
Yeah.
Thanks, Dennis. Yeah, Dennis, I think I was answering you based on what I read in the past, but I didn't realize it was actually right below it. So that, yeah, the explanation is right there.
Okay, so I just absolutely completely bombed that quiz. So like, how bad is that gonna affect me? Because like, are you gonna give me any credit for that? Because like, I ain't gonna lie to you, I'm kind of struggling. I'm the only undergrad down here, so it really sucks. I ain't gonna lie.
So for the most, except for the larger quiz we had, all quizzes, I'm giving you the answers in class. And it's more to make you think. It's really, I mean, of course, if you tell me something that's completely wrong and makes no sense, then of course that is like, maybe a little bit more iffy, but I mean, as long as you try it and you give me something that makes sense, I'm not looking for perfect score or, the correct answer. It's more to get you thinking.
Okay, well, mine doesn't make sense.
Yeah, well, I mean, if you wanna chat afterwards, we can return to this and just clarify. I guess maybe like, I know this concept is a little complicated to get. I mean, well, I guess was that Ethan in Tifton?
Yeah, it was me.
Ethan, and maybe others as well. I mean, is it making a little bit more sense or still?
Once you explained it the second time, it made more sense to me.
Well, I mean, I understand how water flows just based off of the first elevation map we did. And that was kind of my point in asking like what these points represent, because I mean, I don't really understand what the point of that was, I reckon, is my interpretation of it.
Yeah, so that's a good point.
It's completely backwards. Like for some reason, I don't know why, but when I looked at that compass thing with the X value, I thought it was inverted. So I was saying that water moved from east to west and not from west to east. I mean, like I can look at that map and tell you the water is going to move from the left to the right. I mean, I know that, but I don't know. Now, like I said,
Don't worry about it. I mean, I can see that you were thinking through it. That's my goal with the quizzes, is just to get you thinking and not to get there is a correct answer, but that's not necessarily what I'm looking for. I just want to make you think. That's all.
okay.
Yeah. So, I guess one point that you brought up, Ethan, is if we go back to the elevation map, You know, and we just, because I mean, these things are connected, right? Because flow direction is being calculated based on elevation. So they should make sense, right? So if we look on this map here, we do have higher elevation with the yellow colors on the western side of the field and lower elevation on the eastern side. So even if we did not calculate flow direction at a field level, not at a pixel, so flow direction is at a pixel level. At a field level, we would kind of, you know, gather from this that water would move from west to east, just looking at the elevation. Do you agree? Or does someone, is that not clear for someone?
Yeah, no, I mean, that makes sense. Like I said, I understand that aspect. I reckon just in the reading stuff, for some reason, I got turned around and I thought it was like inverted. So I don't know where that comes.
No, and that's completely fine. And again, you know, we don't have a north arrow here, and that question that Tyner had earlier, as far as like, which should we all, can we assume that it's facing north or not? You know, it could have been part of that confusion as well. So no worries. I mean, I understand your thought process, and that's
That was my question too before we took it, which way it is true north. I was trying to understand and help me figuring that out.
so the question of like which way the map is facing.
Yes, and I was assuming that the top of the field was north, but I was just wanting to double check.
Yeah, and that's a safe assumption. Yeah. So normally, even though we don't have a north arrow here, but normally the GIS, any GIS by default would have your maps facing north, right? So with the
Yes, sir.
north arrow, the north arrow would be facing up in the map.
Thank you, Dr. Bastos.
Absolutely. Anyone has, yes, Peter.
So for example, now we move example. So it means that for the water direction, for example, we'll always check one, right?
For the water direction, most of the pixels fall in that class 1, which means moving towards east.
So, okay,
No, like, but can you explain this to the putting X as a number? Oh, sorry, then you can. Sorry.
Lots of questions. That's great.
so, okay, now we see that, it's moving in the east direction.
Mhm.
So let's assume like the same figure, but water was moving on the west direction.
On the, like moving towards west. Is that what you're saying?
Yeah, toward west.
Mm-hmm.
And so now we see it's moving toward east. So let's assume now it was moving toward west.
Mm-hmm.
So like considering number one, what do we say?
So if you think of it, like if we, so Peter is asking if water was moving west, what would that mean? We do have that situation here, right? So if you look again on the documentation, well, let me ask you this, Peter. If you are sitting on X, on a pixel X in the middle, and you're telling me water is moving west, which number will that pixel that you're sitting on receive? 16, right? Because 16 would be going on the western direction. So that is, we have that class right here. So those are the pixels where water is actually moving west. So for this field here, if you look at it, we have pixels moving where water is moving from that pixel towards every direction, right? We have all directions represented in this field. Maybe that wouldn't be the case, right? Maybe you have a field that's so completely like sloped in a way that every pixel is moving water in the same direction. That could be, right? You could have maybe one or two classes here instead of all of them. But for this field, we have pixels represented or representing every flow direction class. So 16 pixels under the 16 plot are the ones moving in the western direction. Did you get it? Okay. Yes, sir.
Is there a way to arrange that to put like one in the 32 slot so it does eventually look like this? You feel what I'm saying?
I see. Yeah.
Match what that is saying. Like, is there a way to?
It's just like reconfigure the map.
That way, like, you're looking at it, instead of like
Yeah,
one actually being on like the northwest side, it's actually is as far as that area.
I see what you're saying. Okay, so Tyner is asking, perhaps that's also part of the confusion when we created this, when I showed you this map here. So Tyner is asking if there's a way that we can reconfigure these maps here and have the actual, so 1 would actually be where 32 is, and 2 would be where NAN is, and really have the map, the way that the map is showing here, match what this matrix here is showing us. There is a way, yeah, and that's a great point. That maybe that's something that, you know, we can even do at some point. But that, yeah, there is a way to do that. Yeah. Yes, I'm in there.
Can you explain like with the value of X? So like just putting a random number like 30, then also the largest difference will be 30 minus 1 will be 29. So what will be moving from center to the east? So what will be the number? Because always the biggest difference between 1 and that number will be like, what will be the number when what is moving in west direction in 16?
So, okay,
It
so
would be next.
let's just go back again to how is this being calculated, right? So it is using elevation. So X here is just a pixel in the middle, right? And this pixel could be anywhere in that field as long as it has neighboring pixels around it. So if it goes to X and then X has an elevation of, let's say, 40 feet. If the water were to be moving in a western direction, then it means that the pixel to its left, if you're facing north, the pixel to its left, so the pixel towards west, is the one that would have the largest difference in elevation from pixel X. Okay, so let's say X is 40 and then pixel 16 here, so the one to the left is like 20. So like 20, there's, I mean, that's a lot of difference for such a close proximity. So let's use something more realistic. Maybe like X is 40 feet, and then on the direction, on the western direction, that pixel is like 38. There are 2 feet difference, right? And everything else around it is 39, except pixel 16 is 38. So then pixel X receives a number 16 because that pixel is moving on a western
So
direction.
like, it's not a number 16, it is just telling the side pixel number.
Is not an angle. It's, I mean, it's really just this is what it means. It's just a direction based on the center pixel.
Why did it don't tell that, yeah, depending on the side?
Yeah, that's a good question, I guess. Yeah, but yeah. Yes, Dennis.
Yeah. Normally when we look on those kind of, because it's visualization, right?
Mm-hmm.
And I assume like those points are like close to each other, so getting differences. If you got, can we display maybe the percent in each pixel number rather than depending on normal visualization? Like for me, if I look at this, I say, okay, maybe number 1 is almost end of number 128. So if maybe I have a percent displaying on those images, maybe I can decide like quickly, I say, oh, okay, this number.
Mm-hmm.
Because I feel like I can miss the answer because of like, I can't count like.
Right.
You see?
Yeah. So Dennis is asking, like, is there a way that we can calculate the proportion of pixels within each one of those classes so we can know for sure which one is the majority class? Because you know, one could think that maybe 1 is the majority class or maybe 128. That's a great question. I mean, if your answer was 1 or 128, you know, I mean, I'm not looking for even though there is an exact answer here, I'm not looking for that. I'm just trying to make you think. But if you told me that the majority was 8, then yeah, I mean, that makes no sense, right? You would have missed that answer, that question. But if you do want to go ahead and calculate the proportion, we did that in a previous exercise. So we can do that. You have the code for that. And if you're interested, you can look back on what we did and use that code. Because we basically did that for a different layer.
Oh, I mean, I was like saying display on those maps.
To display, but how would, so let's say if we do calculate and I tell you that number 1, let's say, is like 50% of the pixels.
Yeah, and then that.
So how do you-
percent is over there.
Over there, where?
Is on that map, like
one is indicating this percent, that one.
Okay, I mean, that's just, there's more steps to that, just because like you have to fine tune the visualization itself. But yeah, I mean, to calculate the proportion, which I guess is the most important thing of your question, we have done that on the yield spatial temporal stability class, where we calculated the number of pixels within each one of the classes. So we have the code for that as a resource if you're interested.
So it was just similar to the last, so
Mhm.
water is doing all the relations in this map, but the
Mhm.
majority of the water was eastern, like, northeast.
Right. Yeah, so Sandesh was saying here, like, for us to just summarize things, so water is moving in all directions in this field on a pixel basis, but the majority of the pixels are moving, water is moving on an eastern direction. That's a great summary.
Northeast, but
Hmm?
northeast.
In northeast, yeah, and northeast as well because of the 128. Yeah, that's right.
Yeah, for me, I just said number one, but when you look on the elevation map, you
Mhm.
see east is like the one concentrating,
Mhm.
but is made up like water can go also northeast or
Mhm.
southeast.
Mhm.
So like if you go away from east, you see like still south east is having a flow and northeast is having the flow. But the concentration, if you look like on a big screen, you see more of the points concentrating on the east from
Mhm.
southeast and northeast.
Right, right. Yeah. No, and again, like if you told me that 1 or 128 were the major categories, that's completely fine. I'm not looking for like very specific. Of course, again, if you told me that 8 was the major category, then that's clearly wrong, right? There's no question that that's not the right answer. But yeah, as long as you gave me something that makes sense, that's what I'm considering. Just wanted to make you all think. So don't, if it didn't answer exactly what we discussed, don't worry. I think all of you gave me answers that make sense, even if you did not get the exact correct answer, but all answers made sense. So no, don't worry about that. All right, this is great questions, great conversation. I actually was not anticipating these many questions, and that's actually a great thing because it means that, we have to clarify some points. So before we move on, any other questions remaining about flow direction? All right, I don't hear anything, so let's continue here. The next step is, so as you realize, as we develop the maps, and especially the individual maps, we were always saving them to an object, right? And why were we doing that? That's basically because I want to combine all these maps into one figure, and to do that, we have to save them in objects that we can then call later. So if you go to the next chunk there, that's what we're doing, is just combining those different maps. That plus that we're using there is coming from the package Patchwork. So remember, we use the plus in ggplot. In that case, that plus is coming from ggplot. But when we're combining ggplot objects, it knows that this plus has to come from the package Patchwork, because that's how we combine plots. If we did not use library Patchwork in the beginning, which we did, and we just did not load the package Patchwork and try to do this, we would get an error because it would try to use the plus sign from ggplot2 package, which is not the one we want. Anyways, a lot of talk, but just if you go ahead and run it, it creates our four plots. Oh, and I just noticed that my flow direction, the color scale is not with the proper breaks. So I'm just going to go back and fix it. Okay, now it is. So just rerun this again to get the proper breaks. And then every time you print a plot, if right after it you run a ggsave, it will export that plot. So I just want to export this into the output folder. I want to call this terrain.png. And I'm giving a width of 10 I think it's inches in this case, and 6 inches of height. If you run that and you go here on your files tab, If you go to output, you should see that terrain.png there, and this is our plot, right? So this is a plot showing elevation, slope, aspect, and flow direction, all the things that we calculated and did in this terrain exercise. Okay, so here's one thing that, again, I want to make sure you all understand why we're doing this in the process of doing it. So right now, all of our terrain objects are raster objects. And it's fine to work with raster. And the reason why they're raster, because that's the output of the terrain function. However, I think that transforming these rasters to vector is actually easier to visualize the data, because then we have a data frame we can look into, because stars doesn't give you that easily. And so I want to basically transform all of these 4 objects that we had into vector, back to vector. So what is happening is right now, as a stars object, they have pixels, right? And a pixel has a value. I want to transform that pixel into a polygon. So imagine that now each pixel becomes a polygon, where we have still multiple values associated with that polygon, but it's just easier to visualize as a data frame. So let's do that first here for the elevation map or data. We come to the next chunk here. That is called IDW_pred, is the name of the object that we created when we interpolated elevation. Right, so this is, again, a stars object. So I want to use a pipe here and transform that to SF. So if you remember, if we're transforming something to SF, we use the function st_s_sf. We do not have to say which columns have the coordinates, because a raster is already a geospatial file, even though it's not vector, but it's already geospatial, so it knows where the coordinates are. But we do have to change a few arguments here. So one of them is an argument called s_points, that the default is true. I want to say false. If you keep the default, it's going to give you point vector file, and we actually want polygons. So s_points equals false, so it gives us polygons. Add a comma, and there's another argument that is called merge, and I want to say false. So we get each individual polygon as its own polygon, instead of having one big object for all polygons. So merge equals false. Finally, I want to add a pipe here, and I want to do a select. So remember, select comes from dplyr. We have to specify dplyr : and then call the function select. And let me just print this here to see. So right now, if we were to stop right before the select, we have the columns var1pred, var1var, and geometry. I want the column var1pred, but I want to rename that as well. So I can just say that I want to select var1pred, but then I can, like, on the fly, rename it as well inside of the function select. I want to call it 11_meters equal to var1pred, meaning that now we're renaming var1pred to elevation meters. So we know what it is, and we know what unit it is as well. So if we run that and we print it, now this is a simple feature, so an SF object of type polygon, so not points, it is a polygon, where we have a column called 11_meter, and we have 4,032 rows, which is the same number of rows that we had for the yield as well. And the reason for that is because we're using the same interpolation grid size that is just being used for different layers. So we're keeping the same number of rows throughout. Okay, so we're basically going to do now the same for slope. So we start, the name of the object, the stars object that has this slope data is called slope. I just want to print that here so you can see it. So it is a stars object. You want to use a pipe, again, st_s_sf. We're going to say s_points again equals to false, comma, and then merge equals to false. And then we're going to plug that into, again, a dplyr select. So dplyr : select. And let's see here, the name, so the current name of this column under this slope object is called PCT. So I want to select PCT, but I want to rename that to slope. So the slope equals PCT. We run that. We print it. And now I just want to talk a little bit about something that has happened here. So the grid that we use to interpolate has 4,032 cells, right? So when we look at the number of cells in the elevation file that we just did above, it does have the same number of cells as our grid, which makes sense. It should have that. However, yes, go ahead, Ty.
Mine says 36.
Yes, that's what I got as well for the slope. Yeah, no worries. That's where I'm going with this. So for slope, we have less number of cells than we did for elevation. Does anyone have any idea why?
I think while calculating the slope on the boundaries, cells are great. You know, they didn't see the outside, the boundaries value. That's why they have the NA values like that.
Yes, that's exactly it. Thanks, Hikar. So let me show you what's going on here. And we can go back to the plots as well, just to visually see that. What happens is slope, aspect, and flow direction are all operations that depend on its neighbors to determine the value of that pixel. So when I'm calculating the slope, for example, or maybe let's go back to flow direction, right? As we were talked a lot about it. So if you go to pixel X, you need to have all 4 neighbors around you to be able to say which direction X is going, right? So what happens is for pixels that are near the boundary where they don't have all 8 neighbors around them, they cannot have a slope, aspect, or flow direction value calculated because they don't have all neighboring cells to be able to do that. So that's basically the reason why for slope here, slope has fewer cells, but also you're going to see the same for aspect and flow direction. And we can kind of see that when we plot them as well. So we see elevation, just going to zoom in. We see elevation is like going very close to the boundary, right? But then when we go to slope, we see that all those cells that before were there for elevation are not here anymore for slope. And the same happened for aspect and the same, or maybe not this. Well, let's check the flow direction when we get there. Maybe flow direction somehow was still able to calculate it. But definitely for aspect and slope, we don't have those cells near the boundary because they didn't have all neighbors to calculate. So that's exactly it. Okay, so we did for slope. Let's go down to.
Hey, Dr. Vesta,
Yes.
really quick. Austin and Miller are having an error, and it says that the column PCT does not exist.
Okay, and that's on the slope one, right?
Yes.
Correct.
So what I would do is add a comment off the pipe that leads into select. So comment that off so you break the flow there, and then run everything that's above. So that should still run. And then when you print that object, so without the select, right? So we stop the flow there, you ran it, and now you print what is slope V is. Look at this column here and see how that's called on your side.
See, they have a _M, but it's different values.
Are you starting with the object slope here?
Yes.
Okay, when you just run slope by itself, so I'm just selecting that object and clicking to run. It is still stars, so it's like harder to see the values. But if you come on the first panel, it does give you the statistical summary, which should match.
I have elevation geometry.
Yeah, they have the elevation _M under their slope for some reason.
Okay, is anyone else having that issue? Just so I guess so for everyone else, if you're following, when you ran slope, well, if you just go ahead and add a comment on that pipe and you stop the flow to go to select and just stop at STSSF, you run that, and then if you print it, do you get a PCT
My
column?
elevation map didn't look like this either.
Say that again?
Like my labels on my elevation map didn't look the same as yours, even though it's coded the same.
Oh, okay, so you mean here, like, so when you print elevation V, the values are the same, but the column names are not?
Correct.
Okay, let's troubleshoot that maybe after class, if that's okay. There's probably something like up above in the code that we're deferring. That it may be easier for me to look at your screen and see what you're getting. Is that okay?
All right. Yes, sir, son. Thank you.
Yeah, no worries. Was someone else also having issues with different values? Let me ask that way. Okay, I don't hear anything, so maybe something very specific that, yeah, we can troubleshoot later.
Okay, I'm using it, but instead of it saying PCT,
Oh yeah, it's probably because we already ran like through with that select, and that select is actually renaming as well. So I think that's probably why you see is low. Okay, so we're gonna do the same for aspect. So I think that was Miller, right? So Miller, for you, you may not be able, I mean, you may still be able to run the following steps, but don't export the layer. Let's wait for that before let's first fix what's happening with you before you export. But everyone else, if you're able to follow, then we do want to get to the end of this exercise and export. So we're going to basically repeat the same thing that we did for elevation and for slope. We're going to do for aspect. I left you most of the code. The only thing we have to change is just remove those 3 dots and replace that by the aspect object, which I think it was just called aspect. So I think that's the object name that we had up from above. Yeah, so we just come here, again, we're transforming from stars, raster to SF vector as a polygon and just renaming the column values to have the name aspect. Oh, and I had an issue there. Let me see what's going on. Oh, okay. Yeah, so on my side is already saying aspect, so I don't need to do the renaming. So I just want to show you what happened. This is probably a difference from my original script where I had the older package version. If I run as what I'm showing you, it gives me an error. It tells me column values doesn't exist. So the way that I troubleshoot that was just to run up until here again and seeing that actually my column is already called aspect, so I don't have to rename it, I just have to select it. So I just delete the equal values and just select aspect. That's what I did. And then that goes through. And then lastly, we're going to do this for flow direction. So maybe my code as I have right now, yeah, well, we'll see when we get there. But so here on the 3 dots, you just delete the 3 dots. And we're going to change this to flow dir, which is the name of the object that we have, flow direction. Again, transforming that to SF, so to a polygon vector file, and then selecting flow direction. Yeah, and if you just have as me, you're going to have to change it because it's already called flow dir before going to the select. So we don't have, there is no values column. So we just delete that and just say select flow dir. And then we print it. Yeah, so it's very interesting that noticing here, if we go to the, so slope has fewer cells, right? So what we were expecting was to see 4032 that elevation had. However, slope has fewer because those boundary cells are not able to be calculated. Aspect has fewer and equal to the same number of cells as slope. So slope and aspect have fewer and the same number of cells. But then flow direction has fewer, but not as many, not as fewer as the other ones, which is probably, again, just the way that the pixels are being calculated and the values are being determined. Perhaps in the case of flow direction, as long as you have some neighboring cells, it would still calculate. Maybe it just doesn't calculate if you have no neighboring cells to go off of. I don't know. we can, if you're really interested in those details, you can read the documentation of the function. They probably explain it there. Okay, so if you were able to get to this point, we basically got our four layers of elevation, slope, aspect, and full direction, all transformed from raster to vector. So now we can really see them as a data frame. It's easier. And now I just want to combine them into one object, where if you think of it, we're still gonna have that geometry column that has the polygon, each one of the polygons of the grid, and then it's gonna have multiple other columns where each column is gonna be a terrain property. So we're gonna have a column for elevation, one for slope, aspect, and full direction. So let's do that and save this into an object called terrain_v for vector. To do that, we start off with our first layer that we just created above, which was elev_v. So just to refresh your mind, elev_v has elevation in meters, and it is an SF object, a simple feature object. So that is vector. That's what we wanted. We're gonna add a pipe, and we're gonna do a join. If you're doing joins on spatial objects, we normally want to use the function st_join to do that. So the first one that I want to join here is the slope. So the object name is slope_v. I add a comma. We're going to change a couple of arguments here. So one of them is the join argument. So the join argument, the default value, I think it's st intersection. We want to change that to st_equals plural. If it prompts you to have to be a function and add the parentheses there, you can just delete the parentheses and just have the word st_equals. And then add a comma, we're gonna change one more argument here called left. So left equals true. I believe the default is false. So we're just changing a couple of default behaviors of some arguments here. So if we go ahead and run this, and then let's just go ahead and run the summary as well. Well, let me see here. I'm just going to run just terrain v. So without plugging that into a summary, just so we see the terrain v object itself. It still has 4,032 rows. It has the geometry, right? And it also has the elevation and the slope column, which we would expect. The elevation coming from the elevation v and slope coming from slope v. And notice how what it did is it kept the 4,032 cells originally on the elevation, which has no NAs. However, as we already talked about, slope and aspect and full direction will have some NAs, especially the ones near the border. So it basically, if a cell existed on the elevation data set and did not exist on the slope, it just added an NA as that cell for the slope column. Okay. So you can just copy the st join that you just did there, add a pipe after it, hit return, and paste it. Because the code is the same, we're just going to change now. Instead of the next one, instead of being slope v, is the aspect v. So we're going to bring aspect into this data set. If you go ahead and run it, and then I'm just going to print terrain v. So you see again, now we have still the geometry column that is the same for all of them, is doing the join based on the spatial location of the cells. And then we have the elevation column, we have the slope column, we also have the aspect column now, because that's what we just did above. And then lastly, if you just add another pipe, hit return, and paste again what you copied the first time, we just want to change slope to flow there _v, because now we're bringing in the last of the four vector objects to merge here. So if you run that, I'm just going to print terrain v again. Now we have elevation, slope, aspect, flow direction, and the geometry, right? So we have everything that we needed as far as this exercise was intended for. Now, if we do run through the summary, we're just going to realize again that elevation, I mean, we get statistical summaries for all of them. We're not going to really get into that. but I just wanted to point out how elevation has no NAs, right? So we don't have an NA row here, but slope has NAs, aspect has NAs, and flow direction has NAs. And that's all because of the way they're calculated and what happens when you get near the border. Okay, lastly here, I just want to come back or go to this next chunk and export this object. So what we are doing is bringing in different pieces of data, processing them, like cleaning, interpolating, and then exporting them, because in a future exercise, we're going to bring all them back, the process versions, and use them in one script. So let's go ahead and export what we did today, or what we finished doing today, as one object. So we are exporting this terrain V, right? So terrain V is a simple feature. Anyone can help me here just to think through what function we will use to export this object.
Right_SF.
Sorry, can you say that again?
Right_SF.
Yes, that's right. Was that Umar?
No, Anis.
Oh, Anish, perfect. Thanks, Anish. That's correct. So we're gonna come here and use the function right_SF. The first thing we give it is the object name that we want to export. That is called terrain_V, the one we just did above. Add a comma. The next thing is we open and close quotation marks to give it the path, the file name, and the file extension, all in the same thing. So we need to get outside of the code folder, // We go inside the data. I want to export this to data folder again, because it's still data, even though it's a process data. I want to call this terrain_V. So that's the name of the file. And then the extension, as you probably already know, is .geojson. I do want to show you. So, well, before I run this, of course, remember to add the comma there. And we always, when we're exporting SF objects, we always want to change the delete_DSN argument to be equals true. The default is false. We just want to have that always there. It's very important to not get the wrong data if you run it twice. So if we run this, we come here on the data folder, we should see a terrain_v.geojson. And I do want to show you something that on your side, you don't have to do it. I just want to show you so you see, let's say you're working with someone and that person asks you for a shapefile, okay? And I only showed you how to use GeoJSON. How would you export a shapefile out of R, right? Very simple. The only difference is it would come here on this, you would just delete the .geojson and just add .shp. That's the extension of a shapefile, right? Which is most commonly used in ACK, or maybe in GIS in general, not just in ACK. If you were to go ahead and run this, look what happened now. So I do have my .shp file, so the shapefile that is really what you launch and open on a GIS, but I also produced a terrain_v.dbf.prj.shx. So we need here 4 files to open that shapefile, right? And again, this is the most common practice. This is common. If you're sharing a shapefile with someone, you will have to send at least 3 other accompanying files. If you send just SHP, they will not be able to open it. You always have to send these accompanying files. And that is the most common thing to see. And again, you can kind of see here why I am teaching you how to use GeoJSON, because GeoJSON basically is just one file. So for shapefiles, each one of these accompanying files has a different piece of information that is needed to open the SHP one. Whereas with GeoJSON, all that is already embedded into one file only. So just for organizing your files, I think is just worth it to use GeoJSON. But if sometime, if any time somebody asks you a shapefile, that's how you would export it. So I'm just going to delete my shapefile and just use the GeoJSON as a touch. Okay, so we did a lot today, right? Or not only today, but in a couple of class periods. So we imported elevation, we wrangled elevation, we interpolated elevation, well, I guess before we interpolated, we did bring in the boundary, created the grid as vector, transformed to raster, interpolated elevation. And then use that raster elevation to calculate slope, aspect, and flow direction. Transform all that to vector, back to vector, merge them into one object, and then export that. So that's a lot of things. And this, I just want to tell a quick story here. So I'm gonna have a study this upcoming growing season that is going to be an on-farm study. And I'm very fortunate to be working with this grower that actually has a lot of these very similar data layers that we're working in class. And he's just sending me them, and I'm like, I know exactly what I have to do to get these processed. And I do hope that teaching you all to do this as well in your careers, you will run into, producers, or maybe your research or whatever it is, that you will see these layers coming your way. And I really want you to, my goal here is to teach you and show you how you would process those layers. So I think it's really, really cool that, I may even ask that producer if he can use his data in this class this year. And just so you see a different field, different set of data, still same data, but different field, different crop altogether. Okay, so the next thing that we want to do is we're going to start talking about, first we're going to talk about soil electroconductivity, how that's important, why we use that in agriculture, how we measure it, and then we'll get into the actual data and processing a soil electroconductivity layer for this field. So for this class, for this exercise, we're pretty much done. I have a presentation so we don't need, any code or scripts for the remaining of the class today. We still have 20 minutes. I think we can get started with that presentation. So I'm just going to launch that here. It is, I want to show you, I posted that presentation to my website. So if you just go on our class webpage, it's right there under today's class. It's just that link. If you just go ahead and open that, if you want to, follow along or take notes, I just want to refresh your head on how to do that. So for us to so this is an HTML for you to take note. Let's see, I think it was, yeah, you push the keyboard letter E to make this like continuous. If you want to have as a PDF, take notes, you push the keyboard letter E, and then you just go on File and export as PDF or print, one of the two. And then you should be able to just print this as PDF. If you do want to change, to landscape orientation, so it looks more like a slide, and how many you have per page, you can also do that. And then finally just save to PDF. So I guess the key thing here is just that you have to push the keyboard key for the E letter to make this continuous, and then print that as a PDF. All right. So again, we're not going to be coding anymore for today, but we're going to start talking about soil apparent electrical conductivity. I guess before we start talking about it, I just want to go ahead and ask, has anyone already had some experience with using or collecting or even using this type of data before? Here in Athens, anyone? So Bo has, Amrinder, David. Okay. Online, does anyone have experience with that?
No.
Yeah, I have installed some of the soil sensors and we are collecting the data, but I haven't yet analyzed that.
Okay, and that was Kriti, is that right?
Yes, yes.
Yes, awesome. Did someone else say something? Okay, so let me maybe ask maybe Bo, how did you use that? Like, what was that?
We did it, in the first machine learning class, fall semester last
Mm-hmm.
We went to, geophysical
Mm-hmm.
research farm and we used what it's called, it had 4 discs.
It had discs.
Yeah, and it ran electricity through the dirt
Mm-hmm.
to this to receive like, resistance to what type of variable.
Okay, so that was probably a Varus, yeah,
like a Varus.
a Varus rig.
4,000.
Yeah, awesome. So lots of people here in Athens saying that. So on the Principles of Precision Ag course last fall, they went to the research farm here at JPC and ran a Varus rig that it basically uses disks to collect EC data. And I guess so. Kriti, you were saying that you used is more like a soil sensor that stays in the soil, is not something that you drag on the soil surface. Is that right?
It's a soil sensor which is 20 centimeter, 40 centimeter, and 60 centimeter below the soil and in the pecan orchard.
Perfect. Awesome. Thank you. And Amrinder, what was your experience with a different system
No,
or
same.
with various? Okay. Awesome. This is great because it really, is a good conversation for us to have and understand the different ways that we can measure this. So let's start talking about what this is. So today, or for this lecture, we're going to talk about what is soil electroconductivity, ECA, or electroconductivity is EC, but then we mention apparent soil electroconductivity that we call ECA. That's basically what we're measuring most of the time. If it's precision ag related, that's the type of data we're going to be using next. So just wanted to make that clear. We're going to have a conversation about how it is measured and why is this an important layer in precision ag. Okay, so to begin with, what is electroconductivity in the first place? So that is basically just a measure of how much electrical current is being conducted through a medium, and it's normally in the units of Siemens or millisiemens per meter. So if you think of it, it's just, again, it's just if you apply a certain electrical current on a medium, how much of that current is going through and ending on another electrode or another part of that sampling medium. So if we think of like both in water and soil and maybe different mediums, that is related to the ionic charges that can conduct electrical current. Meaning that if you have completely pure water has zero electroconductivity because it does not have ionic charges that can pass through that signal. However, if you start adding any type of salt to water that breaks down into different ions, then you start having charges in the water that are then able to conduct electroconductivity. And this, measuring soil electroconductivity was initially developed because this issue of having saline or sodic soils, which is basically means soils that have way too many salts, to the point where it becomes limiting to crop growth and even getting to yield. And so this was initially a way to assess how much soil salt levels there were, so you can determine, I can grow in this soil, or I cannot grow a crop in this soil, or maybe I can mitigate this high salt level in soil and then allow then plants to grow. But what happens here is, if you can just do a quick recall of like chemistry classes, what happens is anytime you have a lot of salts, that salt just holds so tightly to water that even if you have water in that salty soil, plants still cannot uptake that water because it's so tightly related to the salt itself. So the plants cannot take up water even if water is there, because the salts are tightly holding on to it, and plants just die not because of the salt itself necessarily, but because the salt doesn't let water be taken up by plants. So that's the main issue, or that's the issue for which measuring electroconductivity was developed initially. So the way that this has been traditionally measured is you would go to the field, you would take a soil sample, you bring that soil sample to a lab, saturate that with water, and then collect this extractant and measure electroconductivity using electrodes. So imagine that, like, if I tell you that I want to know how much electroconductivity there is on the field, You would basically have to have a grid, have to take a whole bunch of soil samples, bring them to the lab, do this wet chemistry analysis, which is really time consuming. And because of that, is not very feasible for precision ag. Of course, we could still do that in precision ag if we wanted to, but it's not very prone to be used in precision ag applications, at least not in that way of measuring it. So what happens is if you were to do that, go to a field, collect a sample, bring it to the lab and do all that measurement, you're basically measuring the electroconductivity of the extractant, of the water that's coming out of that soil, and measuring that on the water itself, on the solution itself. However, if we can also do EC measurements directly on the field, as we were saying with a various rig, or maybe with a soil probe that stays in the field. And what that is measuring is more apparent electrical conductivity. And yes, you have a question, Dennis? Oh, okay. So we're measuring apparent electrical conductivity of the bulk soil. And the reason for that and why we call that is because now we're not only measuring electrical conductivity of the soil solution as we do if we take the sample to the lab. We're actually integrating over a soil solution. So the liquid phase here, so this would be a soil cross section where number 2 is the soil solution. So electrical conductivity is being conducted through the soil solution itself, but also through other means. So one of them would be this interface that we have between solid and soil particles like clay and the liquid phase. So that is also a path for measuring electrical conductivity. And then it can even be measured, or it can even be affected directly by the solid phase if that solid phase is continuously connected when you're measuring it. So when we go to the field and measure directly in situ, it's not the same measurement as if you were to take a soil sample, bring it to the lab and do the wet chemistry approach. We're actually integrating over the bulk soil when we go and do in situ measurements directly on the field. Okay, so then, the question is, so electrical conductivity is something that we can take a soil sample and then take to the lab, but that's kind of time consuming. We don't want to really depend on that for precision ag. We want to measure that in situ. And so how can we do that in situ? There are basically 3 main methods that we can use here, where one is using electrical resistivity, the second one is electromagnetic induction, and the third one is time domain reflectometry, or TDR, which these are the 3 main ones that you probably have been using. And I would imagine, so Various uses number 1 here, and I believe that probably the one that Kriti was mentioning is perhaps TDR. So let's just quickly talk about these different methods and how we can use them. So a commercial example, again, of the method of electroresistivity would be a Various. So Various 3100 is one of the models, but there are different models. And this is how it works. So you can imagine this being an implement that's being dragged behind a tractor, or maybe a ATV or maybe a truck, but it's something that's being dragged on the soil surface, and you're looking like behind it, like, so imagine that is going like in front of you forward. That's the view that we have here. So the way that Various works with electroresistivity is that it has transmitting electrodes. So it would be, in this case here is showing this one being the transmitting electrode that is basically a disc. You can think of like a tillage disc, similar to that is like just disking the soil and is emitting electricity at that point of contact with the soil. And then that electricity is basically traveling through the soil, integrating with the electroconductivity and resistivity of the soil. And then that signal that passes through the soil is then received at different disks. So this here we have a transmitting electrode, and then this would be a receiving electrode, and this one as well would be a receiving electrode. So basically the signal leaves the transmitting electrode, it integrates the resistivity throughout a given soil layer, and then travels all the way to the receiving electrode. And that difference from how much is being emitted and how much is being received at a given receiving electrode is then related to soil electroconductivity. Because the more the soil conducts electricity, the more signal will reach the receiving electrode. And if you notice here, there are multiple discs on this image, but just to show you one feature that Varius has that others may not have, is if you have a receiving electrode that is very close to the emitting electrode, the signal is integrating over a shallower soil depth, right? So let's say this signal is leaving here and is being received by a receiving electrode that is very close to it. That signal is being integrated over a shallow soil depth. However, for receiving electrodes that are farther away from the emitting electrode, that actually allows it to integrate over a larger soil volume in depth. So emitting electrode being close to receiving electrode gives you data about EC at a shallow depth. Emitting electrode being farther away from the receiving electrode gives you information about soil EC at a deeper depth. So we normally get at least a couple of depths of data when we run Varius. Let's see, what time is it? Okay, 11:05. We can keep going a little bit more here. So the next method to measure EC in situ is using electromagnetic induction. So one of the commercial examples of this is Geonyx EM38. So this is equipment, we have both of these equipment in our department from different faculty. So maybe if you worked in soil physics with Dr. Gore, she has a EM38 that she's been using. It has a similar concept to the Varius, so the electromagnetic or the electrical resistivity approach. But there are a couple of differences as well. So one of the differences is that now the electromagnetic signal is being emitted by one coil and is being read by a second coil. But normally there are not multiple coils that can give you data about different depths. It's just like a transmitting and a receiving coil, meaning that you do not get data for different depths in this case, as we would with the first case, the electroresistivity with the Varius. Also, another difference here is that the electromagnetic induction method uses induction, so it means that it does not have to even touch the soil. In this case here, you can kind of think of this as being, so this right here is the equipment and is just being dragged on top of the soil, but is not cutting through the soil. It has no discs. It doesn't depend on that close contact with soil particles. Which, I guess could be a pro, could be a con, depending on how you look at it. So on the Varius side, I'm just going to go back a slide here. On the Varius, on the electroresistivity, the discs have to be cutting through the soil to have that soil contact and give you a reading. Whereas on the electromagnetic induction, it does not cut through soil. It's just doing that through induction. So that's one of the differences. And also, we don't get multiple depths with the electromagnetic induction as we do with the resistivity in situ method. Lastly, we have time domain reflectometry, or TDR for short. If you've used this, you probably heard the acronym TDR. So this is just one example, and it can be measured in a few different ways. But this is one example where it is basically an equipment that is being carried by a tractor, and it has two rods here. So you basically insert those rods into the soil. One of the rods sends us a wave signal that interacts with the soil, and then whatever is left of that interaction is received by the other rod. And again, this difference between what's sent and what's received is then related to soil electrical conductivity. In this case here that I'm showing you it is in situ, but as you see, it's not like on the go. You cannot drag this over the soil. You have to like drive to a point, stop the tractor, lower the probe, take a measurement, bring the probe up, go to the next point. So even though it is in situ, is the least scalable of the three methods that we're talking about here. I think this is a good stopping point. We're gonna then discuss what affects soil ECA afterwards. And this only has like 6 more slides. So next class, we're gonna finish this presentation, understand what are the main drivers of soil ECA, and then we'll actually do the data processing as well for this type of data. So thanks everyone. If you have any questions, we don't have to take attendance today, as your quiz was part of that. If you have any questions, I'll be here for another moment. And Miller, we can connect by Zoom if you wish. Just send me a Zoom link, an email with a Zoom link. We can do that. And if not, I'll see you all Wednesday or Friday.